Professor Tong, Julene Tong, goes by the name Julene. She joined Georgia Tech last year. She was previously at the University of Florida, but she actually earned her master's and PhD here in Georgia Tech in chemical and biomolecular engineering. She earned her BS degree from Changsha University and Changsha University of Science and Technology in China. She's worked at, in addition to the University of Florida, she worked for a while as an engineer at CH2M Hill.
Okay. Thank you very much, Mike.
Yeah.
Thank you. So firstly, I really apologize. I just thought about it because I have a machine learning center asking me to do a presentation. So I'm totally confused. So then I thought about it's March 1st, not March 2nd. So today I'm out of town in a hotel. So I mean, right now I just I think Mike already mentioned that I joined at Georgia Tech January 2022. So originally I was worked in agricultural and biological engineering at the University of Florida for my assistant professor and associate professor about 10 years. So today I would like to talking about my research about waste valorization process for biochemicals and functional biomaterials. So I put data driven there because recent 2 and 3 years we really using the machine learning or other method process control in the waste valorization process. So hopefully I can. So you can see my screen really well, right?
Yes.
Okay. So firstly, my research mainly focuses on sustainability. So if we're talking about sustainability, we are thinking about all these buzzwords like climate change, decarbonization. How can we get enough food, safety food for the growing population, clear water, energy security, all these things. But we really needed to thinking about is our resources. So all related with resources. That's the reason like recent years I started to look at the use of the waste material as starting materials. So we call it like a Biowaste. So firstly, if you look at this left figure, it's showing like United States and China is 2 big countries to contribute the most solid waste. So like United States generated 624,000 metric tons per day of the solid waste. So if we look at this solid waste, so you can see the Biowaste, maybe they have all different kind of agricultural residues, forest residues, even animal residues, and also, okay, so if we look at that, so they are all different kind of Biowaste and also plastics, they can be recyclable and using as the raw materials as well. If we look at the composition of the municipal solid waste, they're about 70% from the paper products like packaging, many lignocellulose and food waste, yard and wood waste. 30% is about plastics, rubber, textiles, glass, ceramics, and metals. So here I just want to show like for this year's all different kind of the renewable resources or biowaste we have used. For example, we have using like mainly we use biomass include residue cellulose, lignin, and the residue protein, and fatty acid, glycerol from biodiesel process, chitosan and chitin. I have one project focused on this, make the nanomedicine based on this, and the starch. We also use isopropyl and acronym because these 2 monomers can be derived from the biomass. Okay, this figure I trying to show you a big picture what my group do. So my group mainly trying to focus on using the renewables biowaste through different type of the conversion process to make value-added bioproducts. simple ways like this. So one big part of my work is functional biomaterials. For example, the first project is showing right here. It's like a Mars greenhouse anti-UV biofilm. I think this is almost my first project from NASA. The functional biomaterials, the first project I got is like making the greenhouse anti-UV biofilm. We use the lignin as starting material because this project, the concept is very interesting. So we are looking for, we seek the way to make the anti-UV biofilm. So this film can coat it on the greenhouse glass. So then, because on the Mars, the UV is 3 times more than Earth. So this is because Florida have a big NASA center, so we collaborate with that, use their incubator, so to did this type of the kind of research. So in the future, if we want to migrate it, Earth people to Mars, so we can grow the in this special greenhouse for the vegetables or whatever food. Also, my group also working on the smart sensor for food safety packaging. Today, I will use an example to show this. And also, as I say that, we also make the nano bio antibiotics using the biomaterial like chitosan or alginate as a starting material. And recent years, I really trying to use the waste as a starting material through the different type of conversion or fabrication process. We can make the like bioabsorbent or fertilizer, so that can be used for clean, recycle the waste like a phosphate or nitrogen from wastewater or from the waste soil, and then we can go back to use these nutrients back to the croppers. So to grow the croppers. So we call the waste treat waste nutrients recycle. So and my other big part of work is platform biochemicals. So we're trying to, I mainly focus on oxidative catalytic degradation of the biomass or mainly lignin from the biomass, make different type of the aromatic monomers. So these aromatic monomers can be used as a jet fuel precursor, or it can be used for making the bioplastics like tetrafasic acid that can be used for the PET, and also we can also make phenols, so that can be used for the biostimulator to grow croppers as well. As I mentioned that, so recently my research also included the data. So we are looking for the how can we control the feedstock uncertainty using the sustainable process modeling and optimization methodology. Okay, the first one I want to mention that is like Biowaste derived nanocomposite for environment application. So the resources you can see we have used like a peanut shell, we can use like shrimp shell, we can use animal manure, we can use like glycerol from biodiesel, and we can use different type of agriculture and forestry residues. So using these materials, starting materials, so the method we use is like we do nanoscale self-assembling or maybe molecular level synthesis. So we have doing different type of the like nanocapsules, co-shell structure, and also we can do the molecular self-assembling. And then the application we focus on for this part of research. So we have made like soil amendments or micronutrients, fertilizers for agricultural use. So, and we can also made some like intelligent food packaging materials. And also the sensors as a food safety and food spoilage detection. For environment use, we make different type of the completely bio-based polymers to replace the petroleum-based polymers. And also we have been applied different applied this one as for the pollution removal, like in the air or in the water. Okay, firstly, I would like to use one of my examples to show you. This one is using the glycerol from the biodiesel. because glycerol is occupied 1/3 of the biodiesel raw materials, and after the biodiesel synthesis, 1/3 of the materials left, that is glycerol. So we're starting from the glycerol to make the biocomposite film sensor for food spoilage detection. So this research is supported by my USDA and DOE grant. So the goal of this project is like, firstly, we synthesize a pH-sensitive biofilm by nano encapsulation. So then we're trying to develop a user-friendly device to communicate food quality to consumers. So the basic idea is showing right here. So firstly, from the biodiesel, the glycerol, we separated. Firstly, we synthesize the triacrylate based on biodiesel, and then we make the pH-sensitive co-shell structure using called the mini motion polymerization. So we encapsulate food safety dye inside this nanoshell structure. So then we make the film. So the film, we just adjust our recipe, make sure the film have the appropriate properties, so which can slowly release and controlling release the dye, so they can show in different colors. And then we designed we call the RQ film. So the film, so we make this we make this film that can be detect the precisely pH change. So based on this precisely pH change, so we can not only use this one as a film packaging materials, but we can also to detect their food freshness as well. So why we use this like a highly pH sensitive film for food spoilage detection? So firstly, we know the current food spoilage detection is mainly based on two methods. One is directly using the bacterials or using detect their volatile organic components. So we know this method, either you need to know exactly what's the bacterial or what's the chemicals released from your food, and also usually it's very time consuming, it's expensive. And another method is sensory method. The most popular method is called the PCR. Usually this is used for the food industry, but in the food chain, but anyway, it takes about 10 to 20 hours to get the results. So what we're trying to do is like, we're trying to get a rapidly detect food spoilage with immediate contact to the consumers. So like, for example, if you have meat put in your refrigerator, so you can put this film, sensor film on the surface, and then you can just like record the color change, so they can tell you how long you can still put in your refrigerator, and what is the freshness of that. So the trick for this one is like, we're trying to detect the pH in the really small interval, because currently if you look at there are many pH sensitive films. If you look at that, so they usually only can detect the pH in a big range, maybe 2 or 3. So you can already smell it before they detect the spoilage. So that's what we're trying to do. Firstly, we want to get the highly sensitive pH sensitive packaging film, and also we want to make this film we can directly contact with the food, and also even you don't directly contact with food, so you can also detect the volatile organic components from the food to tell the freshness of the food. So here is, as I have already shown before, it's the basic concept, as I mentioned, like the glycerol waste modified, so make as a micromonomer. So the micromonomer synthesized and encapsulated like food safety dye, and then outside is the nanoshell. We can form the nano thickness. So the nanoshell thickness can be adjusted by different kind of the like our micromonomer and the dendrimer ratio, and also by the thickness of the nanoshell. So this can be adjusted to achieve the highly sensitive pH pH sensitivity. And also when the pH decreased or changed, we can see they can also detect the pH change, either decrease or increase. So the spoilage, when food got spoilage, so we can see the color change because of this dye is slowly released from the nano shell on the film. So okay, here is just showing like how can we synthesize, starting from the glycerol. We first synthesize triacrylate, so with diamine. So we form this micromonomer. So this micromonomer is pH sensitive. So when the nitrogen protonated in lower pH, so the shell will be swollen, and then the holes open and the dye can be released out. Here is our results for the pH sensitivity. So you can see this is pH 7. You don't see it's good co-shell structure. The size is about 100 nanometer. So at pH 5.4, you can see the dye has been released out. And the right hand figure here is it shows that you can see using the now red fluorescence at the varying pH. So you can see from pH 3.7 to 6.0. This is based on 10% of dendrimer. So you can see we can identify the pH in really small range. So, and also you can see at a different dendrimer percentage. So the sensitivity is different based on pH. So we can also use the zeta potential. You can see at different pH, like pH 7, different dendrimer. So with the increase the dendrimer percentage, we can see the decrease of the particle size. And also as pH 5 increase the dendrimer, you can also see, but it's also decrease of the particle size. So here is showing because we are not only use this one as a sensor. You know, food unit, they have a lot of like moisture and water, hydrophilic. So if we also want to use this as a film, so here is showing like different type of the copolymers. The first one is copolymer film. The second one is like a dendrimer copolymer film with our glycerol dendrimer inside. And then the third one is with dye encapsulated. And the fourth one is both dye and dendrimer copolymer encapsulated. You can see, because dendrimer is kind of hydrophilic, so you can see the swelling index, the dendrimer DDCP, our final product, they are about 40% of swelling index. But the solubility you can see is below 7%. That means like even our most hydrophilic films, we can see they can meet the requirement for the food packaging. So here is just showing like different kind of thermostability. The first one is showing, you can see the red one here is the one dye dendrimer one. So you can see they are stable. They are stable until temperature over the 300, and they have the TG. The CP have the TG about 80 degrees C. And also the loss modulus and the storage modulus also showing like this one have the stability, thermostability as the food packaging film. So then after that, we trying to using this film we got, because as we mentioned that the film we got, if we put on the meat, we use the pork lion as a meat example. So you can see, we can see different color from different pH. So we connect this data And also we're trying to set up a system. So we have the pattern based on this system. So we're trying to get the QR code system. So we put the film on the we put our sensor film in the center of that. So we put like a green, red, and blue film as a standard film. So then we can using this standard film. So we can cancel all these outside environment like light or moisture or other effects from the outside environment, get us the accurate pH information. And then we use the machine learning method. So then we can record the pH change during the dynamic process. And based on this, so we're using the machine learning method to classify the food is freshness or not freshness. And the only thing we need to use is like our mobile phone with the app loaded in the mobile phone. So then you can tell what the food quantities. So firstly, what we do is like we compose the image features as indicators for food quantity, and they capture the images from the sensory film with precise pH sensitivity. So then elucidate the relationship between pH and storage time to food spoilage with color map. So we build up using machine learning to build up the food quantity with the time, pH, even like temperature, food type, all this information. So here is showing like we firstly use the mini motion we got, because that one you can get the standard corner curve. Here is showing like a standard corner curve based on the our mini motion, and later on we use the pork lion as a sample food, and then use our film to record all the videos, and then connect all the corner information, dynamic corner information to get the corner map. So here is the corner map we got so far. So based on the here is showing like from 2.8 to 10. So of course, in order to transfer this RGB data into the two-dimensional data, we need to use this equation, and then we can generate data at a different storage time. So this is just the release, because we have nano encapsulation. So the dye release will, based on the time, they will have different release rate, and also at a different pH. So we can build up the corner map based on different time, storage time, and a different pH. Here is just showing like, here is based on the standard map we can use as a, we use the film solution. And then we also, as we mentioned that we find the relationship, we use the fresh pork line as an example. So we build up another color map using our sensor film, but we sometimes we use all the data from our lab, all the videos, we connected the data, and also we also search on the literature. My students search on the literature, got a lot of data from literature, and also because sometimes the data for the real case, some data is not smoothing, we use the spleen regression method to smoothing our data, and finally we got the pH from 4 to 7. What is our real food picture color map? And then this one is showing like our quick response QR code design. As I mentioned before, the RGB standard for as a like green, red, blue as a background for the lightning correction or the outside environment correction. And then the app installed in the cell phone obtains the corner and QR information. So you can also use the other like what's the production date, what kind of food type, all this information, putting QR information for that. So so then we link the so this QR code design, after you scan that, will link it all this information, and also to capture the our sensory film information into the database. So here is showing like our food quality classification and detection. So we designed using this like film sensor based QR sticker, so we can got like you can see this blue using the machine learning to do the analysis for the data. So you can see this blue is just like the fresh food, and this red is like spoilage food. So and we can created the boundary for the to detect the food quality. And also this system can tell us what the information. And as I mentioned that we have done experimental, we can contact the food. We can also using the vapor like volatile organic chemicals released from fish. The film is very sensitive as well. So. And comparing with the existing products, our products is faster detection, so can obtain necessary information in one scan, so can get reliable results because we have background and lightning correction. It's user-friendly and detailed information compared with the current available technologies. So existing product, they usually use the NIR spectrum meter. So this is available on the Amazon. So they can determine food quality instead of freshness. So they can also scan food directly, but expensive, have limited functionality. So I think in Amazon it's 2.7 stars, maybe off the market very quickly. So conclusion and future work. So right now we already got the film with precise pH detection for food spoilage. So we can get the barrier films with thermostability. So we can predict the food spoilage for image processing and machine learning approach. So this is users friendly, immediately detect through the QR sticker. But anyway, our future work, what we are trying to do, so we're trying to improve the food spoilage database for our model. So we want to add more food types into the model to make it more robust. So recently we are also trying to simplify our synthesis process using the 3D printer. So and we can make the corners it's kind of array instead of just one sensor film. So we can not just detect the pH. We can look at, we can even based on different dye. So based on the color profile, it depends on different dye. So we can identify, like for tomato, we can identify their mature degree, and also we can identify different kind of the volatile chemicals and the bacteria. If we're using the machine learning to analyze a lot of data based on different dye, because different dye have different sensitivity to the bacteria or special chemicals, not just pH. That is the work I'm trying to do right now. So what time? Okay, so the second part of work, as I mentioned that, so we are, my group also recent 5 or 6 years, we are working on the biochemicals, trying to using the oxidative degradation or depolarization method. So we're trying to make the aromatics from lignin. So why we are interested in lignin? Because the lignin is the most abundant aromatics resources in nature. So they can, but recently the aromatics, it can be used for the medicine or the plastics because of the shale oil. So the invention of shale oil result in about 5% of aromatic decrease and shortage. So that's a big issue. And also the demanding of the aromatics growing annually. So that's the reason. That's the first reason. The second reason is like lignin can be reclaimed from the waste stream and waste stream of the biorefinery, and also can be from solid waste. So they have huge production, but limited market because right now there are many burned as a energy. So lignin valorization process right now, we face the challenges, including like harsh reaction conditions. You need to use high temperature, high pressure. So you need to use expensive catalyst. They have no sensitivity. So you can get a bunch of the monomers and the dimers mixed together, but it's very hard to get the it's really hard to get the specific high value chemicals. And also because of the depending on different type of the biomass, we want to get the robust process as well. So I mean that's my group do. We are trying to use lignin to depolymerize to get different type of the like different kind of like aviation fuel, also got like phenolic acid. So I think because of the time, I will spend 10 minutes to finish my rest of my presentation. Here is like the method we are trying to do. We found like graphene oxide. This is non-metal catalyst with the UHP together, which can depolymer. We use the graphene oxide to depolymerize lignin to the aromatic aldehyde, so we can oxidize this carbon alpha and break down the synectically break down the alpha carbon and alpha beta carbon. But we are not to open the aromatic ring. You know, oxidation degradation many people use a lot for the wastewater treatment. It's just you can really hard to control. And then the second step, the UHP can convert this one into the aromatic acid. So then we can go through a hydrolysis. We can get isolated phenolic acid with the high yield. It's about 15 to 18%. And also we can get like totally 95% of total depolymerized aromatics. So the other part of the aromatics can be used as a jet fuel. So, I mean, this is showing our results. I already mentioned that. So I will not talk about details about this. So mainly it's like we can get about up to 18% of aromatic acid from the lignin, and also the total conversion yield is 95%. So we can almost achieve like a completely utilization of lignin. So another part of research I want to mention here is like because I put data driven in my title. So another part of research recently I'm working on is like I trying to see, because if you compare with like traditional chemical engineering process with the waste valorization process, the big problem will be how can you control your product yield and quantity based on a lot of like variation of your feedstock. So for example, we use the aerobatic digestion as an example. So we use like solid waste, agricultural waste, and food waste as starting material. So so this one is very hard to determine. Firstly, we connect the data, and so firstly we know the main feedstock is carbohydrate, protein, and lipid, and the lignin will not be in the reaction, but they will be in the solid waste as well. So how can you control this feedstock uncertainty to make a stable and robust process? That's what we trying to resolve this problem. And also you need this biochemical reaction is highly nonlinear and a dynamic process, and you have no state of observations. So recently we have collaborated with industry engineering professors. We work on using the reinforcement learning driven Markov decision process used for the sustainable process control. Here is showing like for the aerobatic digestion. So based on the food waste, agricultural waste, and solid waste. Firstly, we got the we converted the elemental. We connect the data from literature for all these different type of the waste material. They only have the elemental results like carbon, hydrogen, oxygen. They don't have a composition. What's the carbohydrate, lipid, and the lignin? Firstly, we figure out the contribution. We figure out the contributions of this feedstock, and then we use the reinforcement learning and driven MDP process. So we're using this feedstock flow rate as a adjust like sludge pump. We can adjust this one. So if we want to control like biogas or biogas mass, so then we can adjust the ratio of this feedstock. So we can control, for example, we can set demand. For example, if we use this process to power a power plant, so we want to make sure we have stable biogas supply, right? But anyway, the feedstock is seasonable. So the storage inventory. So we consider the inventory, so the inventory in supply. So we consider how can we adjust the feedstock ratio. So based on the this one needed, we also combined with the kinetics model, model number 1. And then we can control this sustainable process based on the feedstock uncertainty. So here is showing the conclusions. So what we are doing. So we propose the reinforcement learning-based framework for sustainable valorization process control. You can see this figure showing like if we put the biogas methane production like 150, we can achieve 97% of the like most of our process will be above this average production rate, and also less than 5% of storage overflow, because you know biomass, if too much overflow means expensive price for that. So, and we definitely increased the resilience against uncertainty in both feed composition and supply while reinforcement learning. So, okay. So this is what I just want to use this bigger figure to show in like what we're trying to do. So starting from the bio waste, so like a biomass and the municipal solid waste, we first to do valorization to get the low molecular weight aromatics, and then that can be used for the jet fuel, and we can isolate aromatics, phenolics that can be used for the biodegradable polymers or using for all other different kind of bioplastics. But this process, we are trying to do the data-driven waste valorization process as we're showing the same as like AD process. So here I just want to quick go through this my overall research plan. I don't want to talk about details. So, my research is mainly just like using the natural resources through the different type of the processing. We can get the biomaterials and the biochemicals and the biofuels. So through the multiple discipline transformative convergent research. So here is showing like I want to thanks for my my team, my UF team. I think my current Georgia Tech team. So I need to change the picture because this is our first group meeting at Georgia Tech. We take this picture. I with my 4 of my PhD students. So, and all my funding support, and thank you. If you have any questions, I would like to answer the questions.
Yeah, great, thank you.
I have a question.
Yeah, Dylan.
Or more of a comment. It seems to me that you have a race between the food spoiling and the food being, purchased and consumed. And eventually what you would want to be able to do is you'd want to be able to adjust the price ahead of spoiling in order to make the sale and get it consumed and have a happy, healthy person eating the food. And so I think that the sort of like other side of your model is thinking about how to lower the price so that you can also predict the sale before you predict the spoilage. If that makes sense.
I think originally thinking about example for pork. Before I do this experiment, I really don't know if you put in the refrigerator 4 degrees, one day, your meat is already for pork. It's especially for pork. Your pork is already spoiled. I don't know before my student do this experiment. I think this is like maybe the customer will interested in that, but I know the food company will not interested in that. But another idea right now I'm thinking about, I think I just submitted the proposal to USDA. It's like, I'm thinking about like for tomato, for example, for kind of food. So because the tomato, after you pick tomato up, you put it in the storage, right? So if we can dynamically know based on the temperature and what we know, the freshness, we know the maturity. So we can adjust the supply chain. I'm trying to work on the industry engineering. Dr. New professor they just hired based on the supply chain. He's really interested in that. So firstly, we can adjust the price. So and also we can ship, like we can adjust the price. We can also ship that one. I mean, maybe 2 days later they will be spoiled. So we can like quickly ship this one. We can adjust our supply chain. That's what I think. So I don't know if I answer your questions. Yeah.
Yeah, no, I think you're thinking about the same stuff.
Yeah, I had exactly the same thought, but I was thinking about things like avocados or cantaloupe, things that the peak ripeness of the food is maybe not something that everybody knows. So when I go to buy avocados, I don't know how to judge when the peak ripeness is, but if I have a label, I might be more likely to buy it if I knew that in 2 days that was going to be perfect. I might, stage my buying.
Yeah, we can do that. But I just thought about there are some trick right here. It's like if you want to please the customer, the food production maybe don't want to support this technology, That is the kind of tricky things we need to think about. Yeah, I think my previous work, we really got some company interest in my research, like our patent. So that's the reason I want to keep doing this research. So yeah.
I was going to ask, along the same lines, have you kind of started going down the commercialization path for this technology?
Yeah, I think my patent office, they even support us to continue to do this work at UF, University of Florida. He's really interested in that. We also got some company to contact us, but during the COVID season. So because but anyway, right now, I just transferred to Georgia Tech. I have not talked with Georgia Tech patent office yet. So I don't know if they are interested in, maybe I just thought about it. Maybe I got some new patents, so like that. So yeah.
Well, I think there's two aspects to it. One is, one is going the patent route and like doing the that infrastructure first, or the other question is figuring out if there would be a demand for this in the market and who's the customer for it, and is there a business model for it, etc., etc. So I wonder if your students might be interested in exploring the CreateX pathway to see if
Yeah,
there's a
definitely.
for this.
Yeah. Yeah.
But I did have a question. What you were saying? So we have pork in the fridge. It's there for 5 days. I open it. I smell it. If it doesn't smell, I cook it. Now, if I had your film
Yeah,
on
but
it,
that's not
does
true.
the color start to change and it starts going bad earlier than that? And would I throw out more
Earlier
food?
than that. Earlier than that. We found like we put in the refrigerator for the pork. It's not, it's not pork mince powder, it's just a whole piece of the pork.
Right.
24 hours later, it's boiled based on the standard of USDA.
But you
anyway,
can
we definitely eat. So yeah, we definitely eat it. Yeah.
I see.
But anyway, if you boil it, you probably kill the bacteria. So don't worry about that. Yeah.
Okay.
Yeah.
Well,
Because I'm Chinese, right? So we made dumpling. So usually we put on, we take it out from froze one, because that is have high surface area. Sometimes I just thought about if you put in the 4 degrees C, maybe half day is already a lot of bacteria. I just thought about it. It's very horrible. So it's horrible. So yeah.
but so on the balance, do you think your film would lead to more food wastage or less food wastage?
I mean, personally, you want to eat the safe food, right?
Well, yeah, but you've already said that sometimes we eat unsafe food or food that maybe is just beyond, barely beyond, and maybe if we didn't know or we cooked it to a certain temperature, we're okay. I don't know, but I don't know. Are we going to be?
I always eat that kind of pork, right?
Yeah.
Anyway, that's the reason right now I'm thinking about for tomato, maybe later on for the because right now I'm trying to build up a not just pH. So because right now I see my friends in Florida, food science, we are trying to work together. He's already used machine learning method, but he cannot make the stable dye. They use different type of dye. So you can use machine learning, you can tell, you can predict. So we can do that kind of job. So, but anyway, right now the big issue is like, how can you encapsulate this dye in the film? Use like simple method, because my method is kind of complicated. So.
Well,
so how expensive is it to make this film with your method?
I think method you can see they need like right now my method is very several step of synthesis. That's the reason recently I'm trying to use the I'm trying to working with Dr. Qi in mechanical engineering using the 3D printing to see we can encapsulate different type of dye, sometimes hydrophilic, sometimes hydrophobic, sometimes like the mixed dye with hydrophilic, hydrophobic, because they will have different, you can get different corner map based on different dyes. So you have a lot of data. So you can use machine learning to predict, or that's what I think. But anyway, I trying to simplify the process. I just got a PhD student post qualified, then start to do this work. So yeah. Mm-hmm.
Thank you.
Are there any other questions for Professor Tong? I just wanted to ask one last question. Who else are you working with? You mentioned possible manufacturers or food suppliers.
I have not working.
Are there? Yeah, I mean, who else do you need to sort of? I mean, there seems to be an economic question here, an ethical question here.
Mm-hmm.
Who else has to be involved? Let's say you did want to pursue the Create X pathway or another pathway to commercialization in some way. What are all the barriers that you imagine would have to be overcome besides just the technical barriers that you've made so much great headway in already? What are do you see regulatory barriers or policy or consumer understanding, beliefs, education, something?
I think firstly, if the food production people really want to, I mean, this is just like you want to put more strict rules on them. If they are willing to do that, that will be a big question. And also, I mean, of course, customer is interested in that. I mean, like I talk about pork. I mean, everybody. I mean, everybody think about food safety is very important, right? But anyway, we needed to collaborate with the food production, like vegetables, meat, fish. If they want to do that, I think one way I'm thinking about it's like I know government, so the army, they usually store the food. They store the food for the war or for whatever security reason, but they throw it away based on like expiration time. So if we can get more accurate prediction or more accurate way, so we can save a lot of money for them. That's maybe one way I'm thinking about. I'm trying to search for some DoD money, so maybe the government may be interested in that before we go to the commercialization. So that's what I think. So yeah,
That's interesting.
That's a good idea, because you also, I mean, in terms of mission readiness, you don't want people to be sick, and that supersedes cost considerations.
Yeah, and also you can save a lot of money because they throw a lot of food, even they are not spoiled yet, because expiration date is not accurate.
I was wondering if the reverse might happen, that I was at a talk last week talking about how there's all these sell by, best if sold by, whatever, like there's all these labels that don't mean anything. So I was wondering if the reverse would be true with this technology, that you might actually eat something even if the printed label on the package doesn't give you confidence that it's good, in which case it would reduce food waste.
Yeah. I think that the purpose is reduce food waste and also got safe food. So both are important. Yeah.
Well, it's 4:02. I want to thank you, Julene, again. Thank you for sharing your work with us, and it's really interesting. I hope all of you will come back in 2 weeks again, and we'll have another talk from Professor Marilyn Brown at that point. But thank you very much, and I think we're done.
Thank you.
Thank you so much. I'm so sorry for the inconvenience. Thank you.
No,
Bye.
thank you. I think it worked out in the end.
Yeah.
Thank you.
Yeah. Thank you. Bye.